So we're just waiting for the others to come back. They already have been here. Parfait. Bah, ils sont deux. Ouais. Bah, Alex et Elisabeth. Ouais. Bah, j'en aurais peut-être besoin aussi. C'est qui décide. C'est trop proche, on peut l'enlever ça. Hein. On a déjà fait un sound check et tout avec Rémi. Il y a Jacob.
Hello. Nice to
Hi.
Thanks for being here.
Yeah, thanks for thanks for giving me the chance to join remotely. I would have liked to come in person, but I'm now happy that at least I can be part virtually.
All right, no worries. Thank you for being here, and next time for the second PhD. And
No.
Morning.
for the
Hi,
ability. Hi, guy. How are
Hi
you?
there. Good.
Okay, good. So let's maybe.
So we're in advance.
Yeah, let's start in 5 minutes.
Yeah, in 5 minutes. So yeah.
Okay.
Yeah, perfect. Can see him. Allô, allô, allô. I think we will start. So Remy, Kyle, if you're connected, say hi.
Hi everyone, I'm back.
Hi. Is Pedro here? No? Yes.
Yeah, I'm connected. Hello.
Perfect.
Wait, I can't hear you. Allô.
Right.
Allô. Tu m'entends? Do you still hear me?
I don't know where to put it though.
Yes, we can hear you.
All right, excellent. Thanks. Sorry, I had some issue. Now it's good.
Good morning, everybody. Good afternoon, everybody. We have the pleasure to be here for the defense of Julia Linhart. You present your work in 45 minutes and then we'll have a discussion.
Perfect. Thank you. Thank you all for being here. Especially thank you to the jury members for taking the time to attend, and the reviewers for having read my thesis. So it's my pleasure to present the work I've been doing over the past 3 years on deep learning-based, simulation-based inference with applications to neuroscience time series data. So, sorry. As you all might very well know, the goal in computational neuroscience is to try to understand and explain how the brain works. And so one way to do this is to study models that simulate its activity. So for example, take the virtual brain. It's a platform that provides large-scale simulators that was developed over 10 years ago by Girza and his collaborators. And that is now largely used in computational neuroscience to study brain functions like memory, decision-making, or even to identify disorders like epilepsy. So this platform is accessible online, and you can even download for free these brain simulators. If you want to play around, it's pretty cool. And so, yeah, just what I want to say here is that this is amazing work. But I have to disappoint you here because this presentation is not going to be about that. I'll show you something a little bit more exciting, which is how do we invert these simulators? And this should allow us neuroscientists to better understand how these simulators work, and then develop personalized brain models and personalized treatments. So suppose we have such a forward model that takes as input a set of parameters theta and output simulated signals x. What you can see here is the Janssen and Ritt neural mass model. It's a common example in computational neuroscience that is capable of simulating EEG measurements of electrical brain activity. The parameters C, mu, and sigma here represent characteristics like frequency or amplitude of the signal at the brain level. And the G parameter is actually a gain parameter that models the effect of the measurement device, like, for example, amplifying the signal. But so the goal now is to invert this simulation process and solve the inference problem of finding the parameters theta that best correspond to an observation x. And here Bayesian inference is a standard approach to that allows us to automatically find all the sets of parameters that could correspond to the input signal x, and also gives us some notion of uncertainty about what parameters are more likely than others. But so this inference process is not straightforward at all. And lucky for me, it is, oh, sorry. It's okay. So lucky for me, this is not, this is a real challenge because it's the center of my PhD and I have to do something for my PhD. So let's get to it. So the problem here is you can see a black box on the figure, and this is the whole problem. Mathematically speaking, it means that the likelihood function is intractable. It is not explicitly computable. And this renders Bayesian, classical Bayesian inference methods like MCMC not applicable. But what we do have access to is simulations that we can use to implicitly, empirically, model the likelihood function. And so all the sets of methods that exploit this idea of using simulations to solve the inverse problem are called simulation-based inference algorithms. So how does it work? Basically, you just start by placing a prior over your simulator parameters. And for each sample of this prior, you generate a corresponding observation xi. And this gives you a dataset from the joint distribution that can then be used to estimate the posterior distribution. And here, over the past few years, powerful new algorithms have been developed that are based on deep learning strategies. And this is really powerful because this enables you to scale to high-dimensional complex data distributions, such as time series. So an interesting feature here that we exploit largely in this presentation is the fact of that these algorithms are all amortized. What this means is that once the neural network is trained, you can, for any new observations, quickly evaluate it and infer the corresponding posterior approximate. So examples include neural networks that learn the likelihood function or the likelihood ratio and then proceed with classical MCMC, or neural networks that directly learn the posterior distribution. And this works with deep generative models such as normalizing flows or diffusion models. And these are at the center of my PhD. But so what I'd like to highlight here is that as predicted by Cranmer and his collaborators in 2020, these powerful new deep learning-based methods are now increasingly used in scientific applications in fields like population genetics, climate modeling, astrophysics, cosmology, and also in neuroscience. And notably, they have also been already used to perform inference on the virtual brain that I showed you in the first slide. But so this potentially huge impact in scientific research raises an important question, namely, can we trust the posterior approximate that we obtain with SBI? And this is something we address in one last step of the SBI workflow, namely validation. Here we need diagnostic tools to check the accuracy of our approximation and maybe even find where and why it fails so that we can improve on it. But so before I get into any details of my contribution, I want to show you what SBI can look like and what it can look like on our Johnson and Ritt model from the beginning. So what you can see on the figure on the right is the estimated posterior for the Johnson and Ritt model obtained via NPSC, which is a diffusion-based SBI method, and for a uniform prior over the range of scientifically meaningful parameters here on the plot axis. And so the three different blue colors represent three different posteriors obtained for three different observations, X star, that were simulated with the Johnson and Ritt. The simulator here takes as input a set of parameters, the start parameters. And in all three cases, C, mu, and sigma are fixed, and only the gain parameter changes. But what I want to show you here is that the main takeaway of this slide should be that depending on the observation you consider, the result can be very different. Meaning that you can see that the shapes of the posteriors are really different, and they are more or less far away from the true parameters that are represented in black. This can be really well seen for the mu and sigma parameters here. And especially for a case, the dark blue case, where actually the gain parameter is not very well estimated. But you'll see at the end of the presentation why this is something really interesting for us. So anyways, the posterior distribution gives us important information about correspondence between observations and parameters. And this result directly leads us to two important questions. The first one I already mentioned is, can we trust the information that we can see on the plot? And the second one is there a way to reduce the shift and the dispersion that we observe with respect to the true parameters? So the idea of the first question is that if the answer is yes, these shifts and variances actually tell us something about the simulation model and maybe give us a hint to address the second question. But so these main two questions and first results motivated most of my PhD work that resulted in these 4 papers. And today I will mainly focus on 2 of them. The first one proposes a validation method to answer question 1. And the second one, a new SBI method to obtain sharper posteriors in the most efficient way. I will now dive into these contributions and then at the very end circle back to the Johnson-Ritt model to finally answer those 2 questions. So let's get to it. The first contribution is LC2ST, which stands for Local Classifier to Sample Tests. and introduces new diagnostics for posterior approximations in SBI. It's a paper that was published at the NeurIPS conference in 2023. So I'd like to start by defining the objective of this part of the presentation. And indeed, ideally, when we validate an SBI method, the goal is to evaluate the local consistency of our posterior approximation, which is defined by this null hypothesis of equal distributions. What this means is that we want to test whether our posterior approximate that we had obtained for a specific observation X star actually matches the true posterior, and this over the entire parameter space. So the goal of this work was to find a method to test and evaluate this null hypothesis, which suggests to first find a test statistic, a metric, to actually evaluate this equality between distributions. So this question was addressed by the benchmarking work of Luckmann et al. In 2020. They thoroughly investigated different metrics in the context of SBI on different tasks and simulators in terms of whether the SBI algorithms, here you have very different SBI algorithms, converges to the true posterior as the number of simulations used for the approximation increases. And the main takeaway here is just that they identified a metric called C2ST as overall the most adapted metric for this task, as it is simple to apply and easy to interpret. So what is C2ST? C2ST is a method that consists in training a binary classifier to distinguish between the samples of our approximate posterior and the true posterior. And the intuition behind this is that as the distributions become equal, the classifier will be unable to distinguish between the two distributions, and the classification accuracy will be 1/2. So theoretically speaking, this can be explained by an optimal Bayes classifier that predicts posterior class probability of 1/2, so by pure chance. And this is, by the way, a sufficient condition for the equality between distributions. So C2ST is very powerful because it's not only simple to apply and easy to interpret, but also theoretically grounded. However, and unfortunately for us, we cannot use it in the context of real SBI applications because in this case, we don't have access to samples from the true posterior. So the question is, how do we evaluate our posterior approximation without samples from the true posterior? And here, current standard methods solve this issue by taking a new dataset from the joint distribution, a calibration dataset, and evaluate our approximation in expectation over the observation space. But the main limitation of these methods is that they do not allow for a local evaluation, which can lead to misleading results. And as you can see on the plot on the right, this just means that there can be compensation effects where you could have a seemingly valid posterior on average, but it is actually overconfident in one point x1 and underconfident in another point x2. So there have been attempts to make these methods local, and they rely on regression to estimate conditional expectations that should then allow to evaluate the approximation for specific observations X. But they have a lot of limitations still, which make them impractical to use. So they're very computationally expensive, lack interpretability, and still struggle with multivariate settings. So the question we want to answer is, can we use the powerful C2ST framework from earlier, but without requiring samples from the true posterior? And the answer is yes. And this is what we show in our paper that introduces the local classifier two-sample test. And the idea here is actually really simple. We train, again, a binary classifier, but this time we train it on samples from the joint distributions. And here I want you to remember that it is really easy to sample from the joint distribution by using the prior and the simulator. And then we can also leverage the fact that our posterior approximate is amortized, meaning that by conditioning on samples xi, we can quickly obtain samples theta I and have a data set for both classes. So this gives us a classifier that we can evaluate in any theta and any x, and that can then be used to evaluate local consistency. But so how does it work? The very cool part of this first result is that the optimal base classifier that we approximate with training on the joint is actually the base classifier that corresponds to the original C2ST, which means that it's as if we would have trained on actual samples from the posterior. So this gives a way to estimate what we call the optimal or local base classifier by simply plugging in the observation that we want to consider. But the real problem here, or the real challenge here, is how do we evaluate this local classifier, again, without samples from the true posterior? And why is this a big question? It's because the accuracy needs samples from both classes to be computed. And so the original idea from our approach is that we define a new metric that doesn't require samples from both classes and can be computed with only samples from the approximate posterior. So this new metric is nothing else than the mean squared error between the predicted probabilities evaluated on these samples from the amortized posterior estimate and the chance level of equal distributions. And so we show in our paper that this comes with theoretical guarantees, namely necessary and sufficient conditions for the null hypothesis of local consistency. But of course, in practice, you don't have access to an optimal classifier, and you don't have infinite sample sizes. And this is where hypothesis testing comes into play. Basically, the idea is that you will compare the test statistic that you obtain on your samples from the approximate posterior to test statistics that were computed under the null hypothesis. And this can be done through permutation statistics. But anyways, the important part here is that the intuition behind this is that the test statistic is, it's always better if it's lower based on this theorem. And so if it's pretty high, this quantity will be pretty low. And so what you have to remember, the only thing you have to remember for later, is that we evaluate the consistency of our approximate posterior by looking at the p-value and looking at whether it is higher or lower than a given threshold that we call the significance level. And here, for example, if the significance level is equal to 5%, then we can say that we can trust our posterior approximates with approximately 95%. So as a recap, LC2ST is a very powerful framework to evaluate locally real SPI approximation in real applications. And it fills the gap with respect to existing methods by providing sufficient conditions and an efficient and easy to interpret way to evaluate local consistency. What I want to highlight here very quickly as a footnote is that we also propose in our paper an even better version that is specialized for normalizing flows. So yes, check it out if you're interested. But the most important part here is that there is an efficient and practical implementation of LC2ST that is already available in the open source SPI Python toolkit. And this means that now with a few lines of code, we can answer the first question. And I'll move now to the second question, which resulted in a method to provide sharper posterior estimates in the most efficient way. And this is what we explain in the paper, Diffusion Posterior Sampling for Simulation-Based Inference in Toll Data Settings, which is joint work with Gabriel Cardoso and Sylvain Lecorf. And it's currently available as a preprint online. So I'll start again with a definition. What we call a toll data setting is the case where we have access to multiple observations that are independent and identically distributed with respect to a parameter theta star. So the intuition behind this toll data setting is that as more observations become available, the posterior conditioned on these observations, which we call the toll data posterior, should concentrate around the true parameters. And this is theoretically supported by the Bernstein from Mises theorem that actually states that as the number of observation tends to infinity, your toll posterior will start to behave like a Gaussian distribution centered around the maximum a posteriori estimate of the true parameters and a variance that decreases proportional to 1/n. But so the question is now, how do we estimate this toll posterior in the context of SPI? And how do we do so in the most efficient way? So mainly there are two methods that have been used in the SPI literature to do so. The first one consists in directly learning the toll posterior via maximum likelihood estimation. So this is a method called neural posterior estimation. And here we do so by explicitly modeling the conditioning on the toll data set by using a deep set function. But so the main limitation here is that it requires the use of an augmented data set where we have to simulate n observations per prior sample. And if the simulation process is long, this is quite expensive and not practical at all. Also, it's not a very flexible approach because as maybe more observations can become available, you would have to define a new model that you would have to train again because you would have to specify a model that actually takes into consideration the new number of observations that you want to consider. But so the second approach is based on a very simple and straightforward idea that is that factorizing the toll likelihood for IID observations can be simply done into a product of individual likelihood terms, which means that we can then use directly the neural ratio estimation approach, which means that we can just plug in the ratio estimate into the factorization, evaluate it in each observation, and then infer the posterior. But this requires MCMC. Of course, this is not a limitation necessarily, but it's just simply something that we want to avoid in the context of this thesis. So the question now is, can we maybe use this idea of factorizing the posterior to avoid augmented data sets, but in the framework of direct posterior estimation to avoid the necessity of MCMC sampling? So indeed, we can factorize the posterior as follows. First, by simply applying Bayes rule and the likelihood factorization as before. And then interestingly, by applying a second time by Bayes rule, we obtain a formula that depends on only the individual posterior terms and the known prior. However, unfortunately, this proportional sign hides the fact that there are normalizing constants that are intractable. And this makes the direct computation of the toll posterior impossible, at least we cannot do it with an amortized NPE. But so if we go one step further and we take the gradient of this factorized posterior, we obtain an equality. And this is an equality in terms of Fisher scores. And this should put a smile on your face. Why? Because it's the central object in diffusion. And diffusion is a very recent, very powerful generative modeling approach that has gained much popularity over the past few years. So let me open a little parenthesis on what diffusion generative modeling is all about. As Yang Song very elegantly put it, creating noise from data is easy. Creating data from noise is generative modeling. And so this is where in diffusion, the score comes into play. Basically, the idea is that you will add to your training data set progressively noise, and then train a neural network to approximate the gradient, so the score of your noisy data distribution, that can then be used to create new data from noisy inputs. So this comes with two main advantages with respect to other generative modeling approaches, namely a stable training objective, and also the fact that we can use flexible architectures like transformers, for example. So the other thing I want you to notice here is the fact that by explicitly modeling the diffusion process with a forward kernel, this allows us to explicitly directly define a transition from one denoising step to the next. And this is the essence of very powerful diffusion approaches as we know them today and as invented by Song in 2021. And why do I want you to remember this? It's because it's really important for our contribution, because it has led to the development of very efficient, fast, and accurate samplers that we will leverage in our method. So diffusion generative modeling was popularized as state-of-the-art for image generation, but it's now also very important for many scientific applications, and notably for resolving inverse problems like data assimilation, signal reconstruction, and also in SBI. So how do we apply this to SBI? Now the goal is not to generate new images. Now the goal is to generate samples from the posterior. So this means that we need to estimate the posterior score. And the method that was introduced in the context of SBI to do so is called neuroposterior score estimation. And it consists in training a conditional score network on data from the joint distribution. So what this means, it's just that you will have to define a new input for the score model, namely the conditioning observation next to the noisy parameter samples. And also remember again that the joint distribution can be easily sampled from, so this loss function can be effectively computed. So to give you a little intuition on why this works, using Bayes' rule, we can show that this loss function actually corresponds to the original score matching loss function, as if we would have trained on noisy true posterior samples, and again, on average over the whole observation space. But the important part here is just that we now have a way to approximate the noisy posterior score for any new observation by simply plugging in the observation that we want to consider. So the question is, can we use this amortized NPSE approach to estimate our total posterior? So remember the equation from earlier, the equality in terms of Fisher scores for the factorized posterior. What we actually want now is a noisy version of that. And this can be simply defined by plugging in directly the noisy prior score, which we can compute normally analytically, and the individual noisy posterior scores that we now have a way to approximate. But unfortunately, this distribution that we obtain is not the actual diffusion of the total posterior. And this means that sampling from the total posterior will require sequential sampling with multiple MCMC steps. And doing all of that is a method that we refer to as Langevin, that was introduced by Geffner in 2023. And that I want you to remember because we will compare our methods later. So the question is, can we do better? And the idea behind that is that we want to try to compute the actual score of the actual diffusion of the toll posterior. So the idea behind that is that if we had a way to compute this score of the toll posterior with an amortized NPEC, we could just directly plug it into these efficient diffusion samplers that I mentioned before and sample from the toll posterior without requiring MCMC. So this is our contribution, and I will now show you how we do this. So again, the score of the noisy toll posterior, like I mentioned before, cannot simply be obtained by simply plugging in the noisy prior and noisy posteriors. But what we show is that it is almost equal. So we show that there is a correction term, we call it that way, that gives us this equality, that gives us this formula. And this correction term is defined by the backward kernels. So theoretically now, we have everything to solve the backward diffusion process directly. But in practice, we cannot compute the backward kernels, so we need to approximate them. And we propose simply to use a second order approximation with Gaussian backward kernels that are defined for the backward mean and backward covariance of the diffusion process. So this led us to the following lemma that we prove in our paper, which gives us a way to explicitly compute the toll noisy posterior score. So there's a T missing, I'm sorry, through this approximation. And so again, what we know in this formula is the noisy prior score and the individual posterior scores that can be approximated via amortized NPEC. So this resembles really closely to what we saw earlier with the Langevin method. But the main difference here is that everything is weighted with the backward covariances. And to give you a little bit of intuition of how we derived all of this, here are the formulas of the backward mean and covariance that we took from the works of Boyce and his collaborators from 2023. And so what you can see here is that the backward mean depends directly on the score. So that can be associated to the prior or the individual posteriors. And this just means that everything cancels out really nicely and we obtain this approximation. But so there's one last term that I didn't mention yet, and it's horrible to compute. So this was a challenge that we had to face. But fortunately, of course, there is a way to circumvent that. And the idea behind that is that we want to compute the backward covariance such that it's constant, which would render this term equal to 0. So this led us to the following two algorithms. The first one, called Jack, uses the exact formula for the backward covariance that depends on the Jacobian of the score network. Here, to render f equals 0, we just don't propagate through the gradients at all, like Boyce et al. Did in their works. The second algorithm uses an approximation for the backward covariance, a constant approximation. It's an approximation where we just use the formula in the case of a Gaussian posterior, which means that we can just simply compute it by approximating or estimating empirically the individual covariances of the individual posteriors. So this can be done empirically by on samples that we obtain with diffusion with the individual NPECs. And this is quite cool because it directly gives us an f that is equal to 0. So now we have these two methods, Gauss and Jack, to compute the toll posterior and infer the posterior samples. And I will now show you numerical results that we did to compare to the Langevin method from earlier. So we did that considering, besides other studies, Gaussian toy example with a Gaussian simulator and a Gaussian prior. And what you can see on this table is the run times obtained for different numbers of sampling steps for each method, and the corresponding sliced Wasserstein distance that we computed between samples from the approximate posterior and the true posterior, because it's available, because in this Gaussian toy example, everything can be computed analytically. So the first thing I want you to see is that if we look at the same number of sampling steps, Langevin takes much more time than the other two methods. And by the way, Gauss is the fastest one. And based on this observation, we defined an equivalent time setting where we say that, okay, we want to compare methods that take the same amount of time to infer the samples. And here the interesting part is then that because Gauss is faster, it achieves more sampling steps than the other two methods and is thus more accurate. So leaves a sliced Wasserstein distance that is lower than the two others. So the second experiment I want to show you is an experiment that evaluates the robustness of our method. And here I want you to remember that in our tall posterior approximation, there is somewhere a sum over these individual score approximations. So the robustness we evaluate is with respect to the approximation error that can occur when we learn our score. So we define this approximation error in a controlled way with a score network that is just adds a randomly initialized neural network to the actual posterior score. And so by varying the value of epsilon here, we define different levels of perturbation and can see if the methods scale well to them. And what we can see here is that as the noise, the perturbation increases, well, Langevin and Jack are outside of the plot, so meaning that their accuracy just explodes, whereas the Gauss stays accurate longer, so it's more robust. And we did these experiments for many different dimensions of the parameter space to see if it scales well to parameter dimensions. And the result is consistent as the dimension increases and the perturbation level increases. Gauss stays accurate longer than both of the other methods. So the main takeaway here is that, like I said, Gauss stays accurate longer, is more robust, and especially in high dimensions. So as a conclusion, we identified Gauss with these experiments, but many others as well, as outperforming the other two methods in terms of speed, robustness, and scalability to high dimensions. So we now have two methods to answer the two questions. And so I will now get to it. To do so, we infer the posterior of the Johnson and Ritt model from earlier, from the beginning of this presentation, with our Gauss method, which means that we take into consideration multiple EEG simulations and infer the tall posterior. So the first question was, can we trust this estimate? And for that, we use LC2ST. And I told you, remember what the p-value looks like. So basically here, what we can see is that the p-value is above the significance level. And that just means, yes, we can trust our approximates with 95%. The second question was, can we maybe find a way to reduce the shift and the dispersions around the true parameters? And for this, we look at how the posterior we obtain sharpens as n increases. So this is the result we obtain for the different values of number of observations. And very quickly here, you can directly see that, okay, there is some sharpening here happening. So the variance decreases, but there is some dispersion remaining for the mu and sigma parameters, which means that there is still some bias with respect to the true parameters. So we considered a simplified version of the Johnson and Ritt model by setting G to 0 to investigate whether this now gives us a way to get more sharper estimates for the 3 other remaining parameters. So again, the first question, can we trust the posterior estimate? Again, the p-values are above the significance level, so yes, we can trust it with 95%. And now the second question that becomes interesting, can we make it sharper? So this is the result that we obtain. And here you can directly see that, yes, we can make it sharper. So here it's really nicely plotted that we can see that for different observations where n equals 1, we have large variance in the results. But as n increases, we really sharpen around the true posteriors. So there's no indeterminacy anymore. So the conclusion is that of these experiments is that in the first case, we performed inference on the complete full 4D Johnson and Rid model. And this didn't work out really well. So there was some irreducible dispersion for the parameters mu and sigma. The second experiment showed that by setting G to 0, by fixing it, this new simplified version of the Johnson and Rid, there was no indeterminacy remaining, meaning that we could effectively sharpen the posterior estimates. And so in the end, that just gives us some evidence that there is a given correlation or a dependence between the mu, sigma, and G parameters that is commonly known as something we call coupling between mu and sigma and G. And this suggests choosing another smarter way to model our inference problem with a hierarchical modeling procedure. And this was investigated by my supervisor, Pedro Rodriguez. And it's also something that I looked at in early works of my PhD. So this leads me to my conclusion. I just showed you 2 of my main contributions, 2 methods that should be part of, let's just say, a larger effort of my PhD to enhance the SPI workflow, make it more accurate, efficient, and reliable, in order to create tools that should help scientific research. So the first method was LC2ST, local classifier to sample tests, which we showed are theoretically grounded and can be used reliably, and also are very practical to use and come with interpretable diagnostics. So I hope that this method will be the key to guiding better modeling strategies and inference methods in real world applications with SPI. The second method I showed you consisted in trying to improve the inference procedure in SPI via methods that we called Gauss and Jack. And it should sharpen the posterior, and it does so by efficiently handling IID data. So this method directly leverages advances in score-based sampling that are today a main focus of current research. And it also opens up useful and interesting mathematical tools from the diffusion literature that can maybe be used in other scientific applications. So these contributions pose some interesting questions for future research directions. The first question I asked myself is, can LC2ST maybe be used beyond validation to directly or automatically correct the posterior estimator? And the second one related to Gauss and Jack, can this way of approximating a tall posterior conditioned on multiple observation maybe be extended to other compositional modeling tasks where we would have to combine models to find efficient approximations? And finally, the last, a little bit more general question is, can we use these methods and other interesting works in SBI today to actually create useful tools in real scientific applications? So thank you. Thank you all. I invite you to check out the SBI toolbox where there is a tutorial of the LC2ST method, and I'll leave you with that.
Thank you very much. So now it's time for the jury, the discussion with the jury and questions. So first we have the reviewers. Can you hear me? So maybe Karen first, one of the two reviewers. Can you hear me?
Kyle?
Yeah, I can barely hear. I can hear. Can you hear me? But beyond that, I can't hear anything. Am I being
Yeah.
asked?
So, yes. Elizabeth just asked you to start with the questions because you were one of the
Okay.
reviewers.
Okay, that's great. Yeah, so congratulations on the excellent work and the very nice and clear talk. That was it was very nice to see the developments. I have one question. I don't know if you could go back to around slide 33 or 34. I didn't see exactly the number.
Okay, 1 second. So,
Yeah, the ones that had this the p value. I guess it was slide 34 or maybe even 5 with the p values there.
here?
Right, exactly. Yeah, so I mean, so one, I had a specific question and then a more general question. So the specific question is the p-value here. This is it's the local version of this classifier two sample test. But what data is being used here? It's just the specific data that's being used for making that posterior, or you're like, are you scanning across different? You're doing this for multiple values of what the data would be. Oops.
Yeah,
Okay.
okay, it's fine. I was too fast here, I'm sorry. Actually, yes, because you can see a variance, right? So
I see the
yes,
lines.
we compute the p-value actually on the samples that we obtain here. But the variance corresponds to different classifiers that we use that were, so different seeds to initialize the classifiers, because we just wanted to make sure that the result is consistent, right? That we chose the right classifier.
Okay, sure, but yeah, but other than the training the classifier, the p-value is just local for that one particular value of x.
Exactly.
Okay?
So I
So I
mean,
guess that's fine, and that's clear. So then that leads to kind of my other question. I was just thinking that you can go, you have this local version, and then you have a global version where you sort of integrate over all possible x's or something, and that was kind of the original one, which has the issues that you mentioned before. But I was just thinking, if you do the local version and you wanted to kind of scan around the data space and look to see if it ever has a problem, then you get into something that would be, it seems like a multiple testing issue, because if you have a p-value every time, you expect to see, and you scan, say, like, hundreds of different values of x, you would expect some fluctuation at some point. So there need to be some kind of correction, but it's also very correlated, right? So they're not like every classifier at different value of x is completely independent. So I was just wondering if you had thought, it's kind of related to your final comments about looking into the future about using this to kind of maybe directly train or correct for the posteriors, if you'd thought at all about how you might correct for this sort of multiple testing issue in the local version of the classifier two sample.
yes. So indeed, multiple testing is something that has its place here. So what I just want to make clear is that it depends on what you want to evaluate, right? So if you really want to evaluate the null hypothesis for this specific observation, then, I mean, there's no multiple testing. This is quite clear. Now, if you take into consideration multiple observations, the goal is maybe, I mean, it depends. If the goal is actually to be sure that the approximation is really valid for all of them, then yes, you need multiple testing. And then again, I think there is something that was a little bit, I didn't include that, but we did have some results for LC2ST on the Johnson and Ritt that showed the interpretability of the method. And where is it? Here. So here, for example, we compare when you evaluate with SBC on average and what you obtain with the local method. And here I just plot the test statistics that we obtain, and you can see that, yes, of course, for different observations, the value is different, right? So this is not only due to the fact that the observation is different, but also, like you said, the training of the classifier, where the decision function will be different, right? But I think that so I think we have to distinguish between two approaches. One is that we have an observation, we want to see what we can interpret, what we can say for this observation, and then just general testing methods to see if the method really works well on average, or then even be more precise and get something out of it. And I think with LC2ST, something really cool is these heat maps that we can plot, where we can see that if for a given observation, there's bias or over dispersion, or where the overconfidence is actually can be seen on the posterior estimate, and then gain some intuition. I don't think that looking at p-values over multiple observations really gives you a lot of ideas for better modeling strategies. And so if I now go to the perspective on the extensions to correct for the posterior approximate, this is the right figure for it, because the intuition is just that we could maybe shift overconfident regions into underconfident regions and get something that matches the true posterior that way. So this would mean resampling from the approximation with weights that are according to the trained classifier. I don't know if that makes sense. And I think it's a little bit more complicated to integrate that in the training procedure. But I know that methods have been proposed that are close to the idea, like balanced methods that have been proposed recently. So I think it's possible to add a regularization term in terms of cross entropy, but I think we would have to be smart about that. Like how much weight do we put on that term, and maybe also needing a warm-up so that we can be sure that the classifier is accurate enough not to disturb the training of the underlying posterior, right?
Yeah. Okay. Yeah, no, that's thank you. That's all very interesting. And then I don't know what if we go around and around, or if I ask more than one question typically. I have another question. Should I wait, or should I do it now?
No.
Okay. So the other question I had is, when you first introduced the tall data, you showed the formula that had the factorization of the likelihood as just a product, and then you had a formula showing the posterior, where it's basically a product of the individual posteriors, and then you sort of divide out the multiple counting of the prior.
Do you mean this one?
I think, yes, exactly. And then I think maybe also on the next slide, you sort of talk about the missing normalizing. Yeah, this is fine. Yeah. So I guess I had a couple kind of related questions here. One of them is, if the number of IID observations is varying, I lost track of if the approach that you've described is able to handle that in a kind of amortized way, or if it's assuming essentially that the number of IID observations is the same.
if I understood right, here it's just that you add a term in the product, right?
No, I just meant like once you train your model, could you deal with data sets that have different number of IID observations, or is it
right.
assuming? Yeah.
You could redefine this by just considering batches of observations. So conditioning on, I don't know, 2 or 3 observations, and this means that the product will then be there will be less terms in the product because you already condition on 3 observations. Does it make sense? So you batch.
I mean, the formula is clean. I just mean like from the models that you describe later with the diffusion models and things that are amortized, they can still deal with dealing variable numbers of idea. Okay, and then I was wondering.
I mean, do you want me to go into detail, or is that fine? You can just naively apply to the score the idea of using a deep set, and this is where you can handle IID data with score models.
Yeah,
directly.
no, I mean for sure. I mean, you can stick more things into that conditioning, but then like the kind of factor of the number of times you're double counting or multiply counting the prior changes.
I have
But if that, like
on that, maybe that helps very quickly.
Sorry, it was something I was thinking about after you showed it, so I couldn't really look at the.
No, it's fine. So this is what we call partial factorization. I don't know if it's what you mean, but it's about training a score model with a deep set to consider multiple IID observation, and then batching your data set so that in the end, your tall posterior score has less prior terms and less terms in the sum. Right?
That's pretty much what I was after. Okay, that sounds good. And then I was just wondering, in a practical sense, it seems like when you go from a prior that's maybe fairly diffuse to, if you have many IID observations, the posterior can be very, very concentrated. Then you have, that tends to, show up as some kind of, instability, difficulty in training, or, high variance situation in one way or another. And I was just thinking that since you're kind of modeling this like individual posterior, and then you're sort of dividing out the times that the prior has been, counted multiply, do you still see that kind of instability? Or, I mean, do you still, is this way? I mean, I don't know. It's not a very precise question. I'm just wondering if.
Do you mean if there's an effect of the prior, or?
I just mean that as you add more and more IID observations, the posterior is concentrating, right?
Yeah.
So at some point you have this kind of like ratio between what's going on with the prior and the posterior, and you have this factor of the prior to some power, n-1, and it just seems like that could start to lead to, as that term gets bigger and bigger and bigger, it's going to lead to some kind of numerical challenges. But maybe that's like a.
I think that's an interesting question, because I just thought when I did my experiments, I just thought about this accumulation of errors as we evaluate more networks, right? But you're right that there is this factor here that peaks the distribution, and so I didn't analyze that, but it's really interesting, and it might solve issues in the sampling procedure, because what we observed, though, is that as n becomes really big, our approach, or any approach, becomes biased. And I think this can be something that is related to the fact that you are so peaked that you cannot be as precise as you want.
I think that's exactly. I mean, I don't have a very precise question. It's just that the way that problem manifests itself in different approaches is different, and so it could be that here it's either particularly challenging or particularly clean, because it's kind of the fact that you can point to these individual terms maybe makes it easier to analyze that particular effect. But yeah,
so
okay, I think
batching and partial factorization showed that it works better. It would be interesting to see what the actual source of the problem is. I know, of course, the accumulation of approximations error in the learned score is one reason, but it would be interesting to point at this prior term. I agree.
Okay. Yeah, okay, no, that's fine. I appreciate it. Thank you very much for the insightful responses, and I don't have any more questions.
Thank you.
Well, thank you very much. Remy, can you hear me? No.
I can hear you, but you're convoluted with a big Gaussian, so I assume it's my turn, right?
Okay, it's your turn. Thank you.
Yeah, perfect. Thanks. So hi everyone. Thanks a lot for having me as a reviewer. I had a lot of pleasure reading the thesis and listening to this presentation, and it's also an honor to be in this distinguished panel. So I have plenty of questions, which are actually a token of my liking the work. So my first question is, early on in the manuscript, page 14, you mentioned that throughout your work, you're going to use uniform priors over parameters because they are uninformative. Now, as a Bayesian, that kind of tickles my my ears because, well, as you know, like if I put a uniform prior over theta or log theta, I actually get very different priors. So uniform priors are not uninformative in any sense. So what would you answer to this?
Thank you for your question. No, yes, I agree. It's a bad choice of words. It's not uninformative. I think I said uninformative in a more applied science perspective, in the sense that you don't have to have a lot of domain knowledge to define a uniform prior over a range of scientifically meaningful parameters. In that sense, it's what I meant. I agree that it still gives you information, and it also influences largely the shape of the posterior. So
yeah, especially in your samples, in your joint samples, I mean, the role of the prior is going to be important in a different way than it would usually be in classical Bayesian inference, right? So how do you validate the choice of prior?
Yes, I looked a lot on different prior choices indeed, because in this method of having to compute the noisy score, it can be easier or more stable to consider Gaussian distributions than uniform distributions, of course. So I guess throughout my thesis, I had different opinions on different choices of priors, depending on the application. And with my first experiments, it was the uniform prior because I didn't have enough domain knowledge. But in this last work on diffusion, I actually preferred Gaussian priors. So I think if you take large enough Gaussian priors, you don't have the risk of being too overly restrictive. And still have the advantage of the smoothness. So I think today I would go back to Gaussian priors.
All right, thanks. Later on in the manuscript, when you describe hierarchical neural posterior estimation, you say that you learn your conditional model by minimizing an expected KL.
Yes.
Am I right? I think it's page 61. So I understand that this is probably practical in order to derive a learning algorithm, but from a Bayesian point of view, like, why would I be interested in minimizing an expected KL? It doesn't give me a guarantee on credible intervals or anything, right?
So I
think
don't know.
It's page 61. Yeah,
So,
bottom of page 61.
right here.
Yeah.
Right.
Why would I want to approximate my posterior by something that is good in expected KL?
Yeah. This is the trick in SBI, or I think in conditional modeling, which is that you don't have, you have a conditional observation, and you don't have samples from the conditional distribution, right? So if you want to minimize a KL, you have to do it in expectation over the observation space.
But why do I want to minimize a KL? Like, I'm not interested in the KL. I would like to have total variation here.
This is because you use NPE, and it's It's just the maximum likelihood estimation objective of normalizing flows that we use in the method. But so your question is why use a normalizing flow?
Yeah. Oh, like if I take your method, not looking at the details, but looking at its objective, then that's not really an objective that I'm interested in, right? Because it's not going to guarantee that my credible intervals for Q are going to be good approximations to the credible intervals for P.
I agree. This is where diffusion is more powerful, right? Because it actually looks at the total variance and the distance. Very honestly, this first chapter was about investigating this normalizing flow-based approach. And I didn't even know about, I don't think diffusion was even used that much yet. So I didn't even know about that. So I didn't ask myself that question.
So you're saying diffusion models look at the total variation distance?
I think it can be, no, so it's the Wasserstein distance, if I'm not, but I think you can have some interpretation in terms of total variance or theoretical guarantees at least.
All right. All right, thanks. So moving on, so you're dismissing ABC early on in the manuscript, and then as someone who grew up like scientifically in the 2000s, like ABC was the only thing we had on the shelf. So why you're saying somewhere like ABC for hierarchical models is just not possible? Can you elaborate a bit?
Okay, indeed. Previous work identified ABC as too computationally costly or whatever, and I had to focus on something, and so I said, okay, I'm not looking at ABC, I'm looking at these new deep learning based methods. But I thought a little bit about it, and it's just, I think, the main thing that we have to see. Let me take the slide for hierarchical modeling. So just while I go through the slides, the main advantage of deep learning based approaches with respect to ABC is the amortization. Okay, so I think that ABC was dismissed really quickly because of the fact that actually, well, you have to redo sampling with ABC for every new observation, and it takes a long time. And the second thing is that it requires test statistics, not test statistics, summary statistics for the data. And so when you use neural networks, you can actually learn them while training your approximate, your estimator, right? So this is where hierarchical modeling, like we saw it for NPE, meaning creating an augmented data set and having two approximations, one for the global part, one for the local part. This can be directly used in ABC. It's the same idea in having one ABC step for the global parameter and having one ABC step for the local parameters. And it doesn't necessarily require more simulations. But I mean, it can if the summary statistic is not well chosen, especially for tall data sets, and just the main drawbacks of ABC with respect to amortization and what I said earlier, just they stay, right? So especially if you have to do ABC 2 times, you have to do it 2 times. I mean, it's not amortized, and I think that's the main reason why people abandoned it. Yeah.
All right. My next question was on the elephant in the room, that is multiple testing, but I think Kyle already shot at that elephant. But maybe can we have a look at slide 33 again? So this is when you apply LCA C2ST to your score-based algorithm. Yes. So what do you mean by yes, the test passes? Like which X star did you pick there?
So basically, I just wanted to see if all the information that we show later on the plot is trustworthy. So what I look at later on is this plot where I look at one observation and I see some variance, and I look at 30 observations and I see something sharper. So basically, I just wanted to see if I see that plot, can I trust what I see, right? So I needed a p-value for these different number of observations for these different estimators.
Okay, and so when you say yes, the LCS2T passes, it means like basically my blue shaded area is above the dashed line. Sorry,
yes.
I'm just questioning the meaning of the sentence exactly.
Yeah, no, you're right. So it means when I look at one point, one blue point, it passes. Right? So it's not about like looking at the general curve and saying, okay, all of it passes, everything is good. It's more like if I look at one point, it passes, and I can go to the plot and say, okay, I can trust what I see here.
All right.
I put it all in one plot because it's more synthetic.
Okay. And I guess the next question is probably the difficult version of that question, and it's just meant as an opening to discussion. But like one of the foundational arguments in favor of Bayesian inference is the likelihood principle. Basically says that all the information on theta is supposed to be contained in the likelihood function, which is, conditional on the data. So I'm not supposed to evaluate p of x given theta for any other x than my data. Whereas here, your whole method can be interpreted, if I'm not wrong, as a choice, as model choice, basically, that is violating the likelihood principle. So what do you think? Like, am I right? Are we violating this likelihood principle? And is it not? How bad is it?
So I'm not completely sure if I understand, but for me, it's about the point you choose at inference, right? The observation you choose at inference. And so for now, all of the experiments I did were on points that are simulated with the simulator and that are samples from the likelihood. So I think it's not violated, but then of course, I mean, this is the question about generalizability to points you haven't seen during training and stuff. But in theory, if we had the true posterior and stuff, it doesn't violate the likelihood principle. Where it becomes a real question for me is that when you then look at real data and say, okay, I have a trained posterior and now I evaluate it in not simulated but real EEG measurements. This is where there's a big question mark. And not only because basically because the model doesn't correspond to reality, so you will have a gap, a misspecification, and that's a really important question that SBI people ask themselves today.
All right. So you see this step that you're doing with all the simulations as kind of like preparatory, like a preparation, some kind of pre-processing before even actually seeing the true data. And it's kind of you thinking about your likelihood, but in an automated way. Okay.
Yeah.
Interesting. Cool. Next question. Yes. Well, in LC2ST, like the ability, I mean, one of the key points is that you can train a classifier which will be close to the base classifier.
Yes.
But if you can do this, like if you go to slide 9, I think, hopefully I got the right slide number. Yes, perfect. Yeah. But if you have Q and you have the base threshold, then you have P, right? So how is it easier to train a close to base classifier than to actually approximate P of theta given X?
It's not necessarily. Let's just say that of course, yes, you train a neural network, you try to approximate, you try to learn something, and what you implicitly do is, like in noise contrastive estimation, learning some distribution. I agree. And I just think, I think the main takeaway from our method is that binary classification is just something that is really well known. It's one of the first machine learning methods, also with neural networks, that was invented, and people are used to it. They can interpret it. They know which classifier they can use for which problem, and it gives them a way to just challenge the other model that we learned with a different model that we learned, and see if it matches, right? I think this is the main point. It's about having a method that is that comforts people, and also I think I mean, it does have theoretical guarantees, and not all the generative modeling approaches have theoretical guarantees yet. Anyways, it's not about it being easier to train.
All right.
Even though there might
That's
be. Not sure.
sorry.
I'm not sure. It's an interesting question. There might be cases, yeah.
Yeah, I think it's a very interesting one, like to focus on, because it's I mean, it's one of the key motivations, right? Is that you don't want to go for P of theta given X star, so you go at it like indirectly through this classifier, because
Actually,
it's there on the shelf, and somehow it might actually give you a good approximation to the conditional.
Actually, one cool thing though is about, like I said, it's well known, and there's a big literature on it, on binary classification. And so we just train the binary classifier, but you could also enhance the classification task with like unbalanced classification or multi-class classification, and like, that would enable you to integrate more information about your posterior approximate, and I don't know, try to leverage that to get something more accurate in terms of binary classification than you could do in other strategies.
Yeah. All right, thanks. Maybe one last question on the score chapter. Like, in my mind, like, told data actually means n is going to be in the millions, and it's going to be a problem for me even to evaluate the likelihood. But so how would you modify your method in this case? Like, you had this extra slide that you showed to Kyle on partial factorization. Like, how should I build my batches? How big should my batches be? Do I actually gain something? Is there a theoretical guarantee that tells me the optimal batch size? Like, all of these questions
Yes.
come to mind.
Is there a theoretical thing? It's really, I mean, I love your questions because I would love to work on it. But so there was no time yet. We didn't theoretically analyze what this does, but already in the method that used Langevin dynamics by Geffner, they proposed such a method of batching the data and using partial factorization.
Yeah.
They did an empirical study, like experimentally identify which one is which batch number is, and number of observations is the optimal one. And I think it's about a trade-off of indeed, you know, the number of observation that you condition your score model on. So it's about the trade-off of accumulative approximation error that come into play in the sum here.
Yes.
But also the simulation efficiency of your method, right? I think, so in our experiments, we had the same conclusion as in Geffner, and it was, what did we say? It was for 3 or 6 observations. But again, it's not in the millions. We only considered, like, I don't know, what did we consider? 30? So it's not at all the same thing. And it would be interesting to look at. But I don't know. I don't even know. Like the real reason we didn't consider millions of observations is because we know that there is no way to be a lot more sharper after, like, I think 30 observations, or 20, between 20 and 30. So there was no point. And I think in low dimensional posteriors like that, there's not really a point in considering more than 10 in the tens, you know?
Yeah, yeah.
Hmm.
All right. But that would be an interesting question. Anyway, I'm good. I have plenty of other questions. I really like that you used the sliced Wasserstein and the MMD to validate experimentally. That was also very interesting. But I'll stop here in the interest of leaving some time for the others. Thanks again, and lots of interest on my side.
Thank you very much, Remy. Now we can have Jacob Macker from University of Tübingen, that's Institute. Do you hear me, Jacob?
Yes, I think I can understand that it's my turn now. Yeah, thanks, Julia, for the excellent presentation, and it's really been a pleasure to be part of this. Also, in the discussion section, which in part Kyle and Remy already touched upon some of the points that I would have asked about. My first one was going to be to talk a little bit more about the local C2ST, and the question that I wanted to ask, which I guess you already anticipated in your last slide, and that you already spoke to with Kyle, is the question sort of what if the local C2ST is sort of problematic, how should you update your posterior? So let's not talk about this because I think it's already been talked about a little bit. What I want to talk about is the behavior of C2S2 in high dimensional problems. So one thing we've observed in other contexts, or I guess also in this benchmark, is when your problem is too high dimensional, then C2ST is just extremely sensitive in the sense that if you have just tiny errors in some of your dimension, it just completely already goes away to 1 or to 0. I mean, in principle, if you had 1,000 dimensions and your distribution is perfect in all but one, but it's wrong in one dimension, your classifier can classify completely despite the fact that your posterior is almost perfect. So can you sort of comment a little bit on maybe your empirical experiences with the behavior of C2C in such problems, and do you have a proposal for it to have a sort of a less sensitive or more benign way of discriminating distributions?
Okay, so what you're saying is that C2ST is too discriminative?
Yeah, I mean, sometimes you want this, but sometimes you sometimes maybe you want to be more graded in this.
Yes, it's true. C2ST really, I mean, we can, I don't know, you read my thesis, so we did these kinds of experiments on the power of LC2ST with respect to C2ST. And you can see that it's indeed always discriminate, like always rejecting the test, at least for the accuracy-based version. And so this is a question that also I talked to the author of C2ST, and he asked me the same question. He asked me, yeah, C2ST is too discriminative. How would you regularize that? How would you treat that problem? And at the time, my answer was LC2ST is already kind of regularized because we have we're training on the joint, and this is a more difficult task, I think, than just low dimensional posterior samples that we distinguish. And well, I think it just in the problem that we formalize, it's already a little bit. It's a little bit less discriminative than C2ST. At least that's what we observe. So how would we? I think the interesting part of your question is how would we change LC2ST to be more? I don't know. I just have to think about the balanced SBI methods that define a way of having balanced classifiers. balanced classifiers, they define it with something that is that restricts the classifier from, like you said, not saturating on 0 or 1, but being in balanced probability estimate class predictions. So I think that would be one way to look at this regularization that is used for NRE and apply it to C2ST maybe. That would be my first thought.
Okay, and I have a second question on if my memory is correct, then you train the classifier on data that you didn't use to train your original density estimator, your original. So I mean, I guess it's always good to have sort of independent train and test sets and whatnot. But in this specific case, why is it important that the calibration classifier is using a different set of simulations than was used for likelihood inference, in particular, assuming that simulations are expensive? So is that really needed, and what goes wrong if you train on overlapping or even on the same data?
Okay, for me, it was obvious we had to train on new data to avoid dependencies that are not like that are coming from the fact that we train on the same data. No, but I think it's because also the LC2ST has to be able to generalize to new data, and the classifier that you learn depends on the estimate. And if the estimate is just trained on data that it already saw, I think there will be an issue. So I understand that the loss function is a different one and you optimize different parameters. I understand that, but I don't know. For me, it's important to have a new data set. To calibrate.
I mean, you're always on the safe side if you have a new data set, right? I'm just asking sort of, is there a concrete reason in this particular case, other than the general principle of sort of trying to be conservative and train things on predators?
No, so it was really about we want to validate a method, so we use a new data set. I didn't analyze the effect if you would have used the data we trained the estimator on. But where this becomes actually really crucial is if you then try to integrate C2ST as a regularizer, right? So, I mean, when you do that, you use the same data because you optimize at the same time. I agree. But so you don't. I think the method as we have it for now, it's a post-training way of. Okay, I think I said something that I didn't want to say. What I actually wanted to say is not about the training and the regularization with C2ST. It's about the post-training correction with, like, for example, importance sampling. And if you do that, what you do is calibrate what you already estimated during training of a normalizing flow, for example. And I don't see how we can dare use the same data set as we trained our estimator on. So I think that answer just gives, for me, the idea of we evaluate a method and whether we try to correct the original estimate or not, we want to have some new sense of what's happening. And so new data. But it's an interesting question. I never asked myself that.
All right, thanks. And I have, I guess, 2 questions on the second part. So I was wondering whether you could comment on the performance between Jack and Gauss, and you argue that Gauss works better, and we've built. I mean, actually, 2 members of my group have built on your work and sort of in a different way, but they also find this. It's not entirely clear to me why. So do you have an intuition why Gauss works so much better than Jack? This would be sort of the first part, and the second part would be sort of the limits of this, right? Sort of as you scale up, as you scale up your number of n, then the approximation breaks down. We've spoken about this a little bit before. It might have just, the boring answer might just be that it gets too concentrated. But okay, maybe let's do the first question first and then ask the second question.
So the reason for the Gauss algorithm was the Jack algorithm. So just meaning that the intuition is that taking the gradient of a neural network is not always very stable. It might not really, I mean, for me, it doesn't correspond to the actual gradient of the score, right? Taking the gradient of a trained neural network might not represent the gradient of the function that we approximate with the neural network. So this is one issue. So the stability and actually the accuracy of this gradient. And then also I feel like it's a little bit cheating to just not propagate the gradients. But anyways, that's something else. So we just wanted to see if there is maybe a way to circumvent all of this and just define something really easily, which turned out to work really great. So that was really cool. So let's just say it like that. But I think indeed, I mean, the real issue here is that Gauss is an approximation. So if you take different posteriors that might be really far from just a Gaussian, this can be a limitation. And this is where Jack still is actually the real way to do. So I think that if the question is, can we do better than Gauss? I think it would be going back to Jack and find ways to make it more stable, maybe to compute the gradient of the score or define the score differently. I mean, also, I think this would be maybe your second question. There was a hypothesis here in our lemma, right, about the positive definiteness of this term, which relies on the positive definiteness of the backward covariance and the real approximation. And this is again where I say, when we compute this with the gradient of the score, this term might not be positive definite because we don't actually evaluate the gradient of the score, but something approximate. So this can be unstable, and I think there can be ways to circumvent that. Yes.
Yeah. So did you observe that when the Gauss method breaks down, these were really cases with non-Gauss, I mean, at least anecdotally, are these really cases where the posterior is more non-Gaussian, or are there other reasons that sort of make this, or maybe some boring just accumulation of error as you increase the total number of samples or total number of data points?
Specifically for Gauss?
Yeah.
If there are other reasons so that it would break, you mean?
Yep.
Okay. So again, yes, accumulation of errors, maybe not a posterior. I don't know. Honestly, I don't know. Yeah, I mean,
it's fine. Sorry. I mean, it's not something that.
I think one thing I could say is that there's even more approximation error because we use the NPSE to approximate this covariance as well. So, I mean, if you have a well-trained score network, I don't think that's an issue, but as soon as you have issues with your score network, there will be scalability issues. And but anyways, if you have issues with your score network, all of this doesn't work. So yeah, I don't know.
Okay. And I have one final question. So simulation-based inference methods, in particular neuroposterior estimation, have sometimes been reported to be quite sensitive to model misspecification. So do you see a difference for the score-based method? Do you see them more or less sensitive to this? Or is that something that you didn't investigate?
Model misspecification for score-based methods. I didn't investigate it, but let me think about it. So your question is if it's if depending on the method you use in SBI, they would be more or less sensitive to model misspecification.
Yes. Yeah. And in particular between these two methods you've used. Yeah.
Yeah, I mean, NPE versus score-based. Yeah. I think maybe it would be easier to correct for model misspecification with score-based methods than with NPE, because again of the inflexible architecture of NPE. And also, I think what we could leverage in score-based methods would be guidance during sampling. Maybe. I'm not sure. Like I said, I didn't investigate it, but I feel like if you have some knowledge about what you're trying to sample from, I know that in score-based methods you can use strategies to guide the sampling into one direction or the other of your distribution. So I think as long as there is not a complete distribution shift between simulations and real data, you could use that to get actually accurate samples.
Cool. All right. Thank you. These are all the questions I had, at least for now. Yeah.
Well, thank you very much. Well, it's right now. So first, I want to say that thank you for giving me the opportunity to read your work, because I found the reading very interesting. It's not my subject, so and I find the generative modeling is very fascinating. And I find that the idea of finding guarantees about can we trust results is a good question. So I find that this is very interesting. I have two naive questions. The first one is something I think I didn't understand quite well. In the neuroscience model, you introduced to give ideas of what you want to do. You say, so you have a simulator using the model.
Yes.
But then the parameters are not identifiable. And I don't understand why it would be a problem. Yeah, I didn't understand quite well the problem you asked about that. Because for each distribution that you simulate, you have a set of parameters that allow the same simulation density. And why is it a problem?
It's not necessarily a problem.
So I didn't understand what you discussed.
Yes, what I wanted to show in this slide is just the two questions that motivated my PhD. And it's because basically my presentation was the other way around. My thesis was about looking at the work from my supervisor, which was about hierarchical modeling. And in that work, it was about leveraging the fact that there's this G parameter is global and the other three are local, and creating a hierarchical model around that would allow you to resolve indeterminacies that are the result of this coupling. So this is where they observed these kind of results and showed that you could concentrate around the true parameters. And it's not necessarily something, not being concentrated around true parameters is not necessarily an issue, but it might be something that you want to do because you want to try to see if your model is identifiable, if you can have a unique solution for your inverse problem, something like that. And that was the goal of the work of my supervisor, and I tried to analyze that. And so at the beginning, I tried to analyze that, and I was blocked because I couldn't identify if I could trust actually what I'm seeing, and this is where I did validation then. But so yeah, and in the end, of course, it was interesting to see that if we use TOL data or IID data, we concentrate, but we can really identify the coupling between G and mu sigma.
The other question is very general, but it didn't answer, but I'd like to know what you think about that. At the end, maybe you use your local validation, I think, real data. Then there could be misspecification because your validation is for using material data. Maybe there is misspecification. So what do you think about that?
Yes, it's a very good question. It's a question that people ask themselves a lot in SBI. It's yeah, so all the results I showed you were on simulated data indeed. I did do in my first experiments in my PhD experiments on real EEG data. I think this is an issue. I mean, it was also something that motivated this local part of my my validation method, because if you now have a new data point and it's not simulated, you would want to evaluate in this data point if things work out. And this is where being able to evaluate with C2ST, with the local C2ST on specific observations, that could be really interesting to look at. But then the problem is that, I mean, your classifier is also trained on simulated data, so there will be a misspecification as well. So it's an interesting question. I would really like to get into that for future work, because it's not straightforward how to handle this gap. But there are some ideas in the literature of how do you quantify this gap and how can you maybe add that as a regularization in your training procedure of the posterior. But I feel like it's a very tricky question that cannot be answered easily, and that we have to be careful about that, because misspecification will always be there, because you will always have a model of something that is real, like, right? So I think we need to be careful about saying we develop a method to solve misspecification, because this will never be the case.
So now maybe it's time for the advisors to say something. Maybe we have questions, but maybe we have comments or things to say. Maybe first, Pedro
first.
So Pedro,
Okay. Yeah, I heard my name, so I'll take my lead. So I don't have any question, of course. We already saw several, and Julia, she brilliantly answered all the questions of our colleagues. I just want actually to emphasize how happy I was to work with Julia. It was a real pleasure. That I'm very grateful also, because it was my first PhD student, and to see how much she worked, etc., in 3 years was just impressive. So it's always a pleasure to work with her and learn from her as well. So I only wish good good fortune for the rest, and I'm looking forward to see what you'll be able to do afterwards. So thank you, Julia, for everything.
All right. I guess it's my turn. I think there's some members of the jury who have to go soon, so I'll be brief. I'll say more words maybe later. So I guess the journey for you was as always for PhD, it's not really expected. You sign up for 2 years and you don't really know what's going to happen. And I think you had to find your own path with kind of 2 advisors, one in Grenoble, one sometimes more in Paris than here for different reasons. You had to find maybe Sylvain and other people to kind of help you out. And I guess you were truly an actor of your entire PhD. You shape your own topic. We gave you a few ideas at the beginning, and then you kind of decided what you consider to be important, what was interesting, and traveled a bit, went to see different teams in Belgium, in Germany, and just to make your PhD your own. And I think that's pretty rare. I guess I'm trying to convince myself that not being here was a good thing for you. Kind of force you to kind of develop this autonomy that would be very useful in the future. And I'm really, like Pedro, super happy to what you did. I think your presentation is a beautiful exercise of like showing you everything you've achieved in these 3 years. And I'll say more later, but I think it's enough for now. Congratulations.
So it's time to do the so to have the jury meeting.
Yes. Ouais, on va you're gonna stay here. For the jury, we'll stay here, so we're gonna ask you to kind of transition to outside. We're gonna take probably 10 minutes. Ouais. Il y a des gens qui peuvent mettre les gens en dehors ou pas?
Est-ce que moi je quitte?
Oui.
Oui, surtout pas. Rien. Ok.
Tu coupes pas là.
Je vais couper le son peut-être.
Non,
Moi, je vais parler et il faut qu'on les entende.
Ah oui, ok. Je coupe rien.
Je parle ici.
All right. Can we just have the video here of the jury members?
Yeah.
Okay. No, it's not like we don't see you now. It's something that we have to do on our end just to make sure that we have. Ouais.
We lost Rémi and Jacob. And those in myself.
Alors, faire un mail alors.
Je vais. Non, mais je vais.
Est-ce que faut que je sorte ou pas?
Non, non.
Non, non,
Parce que il y a tout le monde qui est parti. Hein.
ils sont tous
Ah oui, mais
partis.
attendez. Oui, c'est parce que ah oui, c'est parce que t'as pas mis tout. Ok. Normalement, il faut que tu fasses un truc là. On va join frequent room, tu fais stop and join.
Stop and join.
Donc tu peux juste.
Ce que je dois faire.
Stop and join.
En fait, du coup, là, tu peux contrôler l'écran.
Go to the breakout room.
Non, je comprends rien. C'est pas
Appuie
grave,
sur-
Alexandre, il va tout
Mais
comprendre.
pourquoi
Qu'est-ce que je dois faire?
Où est-ce qu'il est la souris en fait?
Joint. Ah non,
Ah,
je
ouais,
l'ai pas là.
ah oui.
Ah,
C'est qui est le hôte de la discussion là? Waouh.
Okay.
Ok. Et donc, le jury a délibéré. Donc, nous avons trouvé que tu as présenté de manière très claire et pédagogique tes travaux sur l'inférence à base de simulateurs à l'aide de réseaux de neurones avec application aux signaux de neurosciences, en détaillant deux de tes contributions principales: la construction d'un diagnostic local de validation de la loi a posteriori estimée et une méthode d'échantillonnage a posteriori pour les simulateurs de diffusion avec observation répétée. Nous souhaitons souligner la qualité scientifique de tes résultats, l'amplitude de tes travaux. Tu as proposé de nouvelles méthodes, dont tu as proposé une analyse théorique, une validation expérimentale, mais tu as aussi contribué à une librairie logicielle qui est déjà utilisée largement par la communauté scientifique, et ça n'est pas commun. La discussion qui a suivi a rendu évidente l'importance novatrice de ton travail, qui ouvre des perspectives nouvelles dans un domaine de recherche récent et fascinant, celui des modèles génératifs pour l'inversion des modèles complexes en sciences expérimentales. Par tes réponses aux nombreuses questions, tu as montré ta maturité, ton autonomie scientifique, l'étendue de tes connaissances, à la fois sur les aspects théoriques et expérimentaux de ton domaine de recherche. Et nous sommes convaincus que tu as devant toi une belle carrière de chercheuse ou d'enseignante-chercheuse, et nous te décernons le diplôme de docteur, le titre de docteur, pardon, de l'Université Paris-Saclay. Donc maintenant, tu vas prononcer le serment des docteurs. Je n'ai pas très mal.
I say in anglais. So French or English, you pick your poison. There's no German. So-
On va le faire en français.
Maybe say it in English for the.
Should I say it in English?
English, so
I was
that-
going to say I'm saying it for the team in French, but
I think say it in English for the jury, so
Okay.
they have the full French experience.
let me see. Where is the English version?
It's just below. It was just where you
Oh,
were.
it's really short.
You can say it in
That's
French.
right. Okay. Okay, sorry.
Yes.
Okay. In the presence of my peers, with the completion of my doctorate in mathematical computer science, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge, to the greatest of my ability, to continue to maintain integrity in my relationship to knowledge, in my methods, and in my results.
Thank you. So I guess you will probably say more things later. We should free the jury. What I like to do is to take a picture of the candidate with the jury.
Yes,
we take this picture and
I just want to say thank you to the jury before that, and especially to the reviewers, right? Thank you so much for reading it carefully. I really appreciate that. It's a real honor. And the interesting questions, I really want to work again now, even though I should take vacations. And Kyle and Jakob, thank you a lot for the past 3 years. It was a pleasure to see you on conferences and to talk science. And I hope I see you again soon. Thank you.
It was our pleasure. Congratulations.
Yeah.
Really
It's
nice.
my pleasure too. Cheers.
don't move. Virtual picture with the jury. Let's see. All right. All right, thank you very much.
Thank you.
Thank you.
All right, cool. Thanks.
Take care. Bye-bye.
Thank you and congrats again.
All right. Congrats, Julia.
Thanks.
All right.
Bye-bye. Bye-bye.
Cheers. Bye.
Bye.
Donc, je quitte.
Hop là.
All right.
Hop. Où est-ce que tu vas, Julia, là, avant de quitter? Qu'est-ce que tu deviens après la thèse?
Après la thèse, je vais faire du ski.
Super.
Non, mais oui, je vais d'abord faire du ski quelques mois, je pense. Et après, non, je vais faire un postdoc, c'est sûr. C'est pas encore à 100% sûr où. Je suis dans des procédures pour peut-être aller à New York au Flatiron. Mais je vais quitter la France un peu,
D'accord.
voir autre chose. Et ben, on verra. On verra.
Ça marche. Si tu veux être Premier ministre, il y a une place.
Ça va.
Mais il faut pas que tu ailles au ski, c'est bientôt, par contre.
Ouais, on verra.
Ça marche. Eh ben, félicitations encore. Et puis, j'espère qu'on se croisera bientôt pour prendre un verre et fêter ça.
Absolument. Merci.
Au revoir, tout le monde.
Au revoir. Pedro, tu restes ou pas?
Je sais pas, enfin, vous allez fêter là, non? Vous allez manger, j'imagine.
On skip les remerciements. Je te fais des remerciements juste à toi.
Ok, non, mais c'est à moi de remercier de toute façon.
Je vais faire des petits remerciements
Peut-être
là-bas,
là-bas.
parce qu'il y a Pedro là.
Ah. Bah oui.
Juste pour vous deux, et après on part.
Ok.
Bah, de toute façon, je vais pas prendre des heures. Hein.
Comment ça?
J'ai plus beaucoup de batterie, c'est la vraie raison. Donc, je voulais juste remercier. Donc, j'ai déjà remercié le jury et donc je voulais vraiment remercier vous deux, Alex et Pedro. J'ai vraiment passé 3 années incroyables et ça a commencé juste avec vous deux. Et je me rappelle très bien de notre premier Zoom et je sais pas, j'avais directement un bon feeling par rapport à notre collaboration. Et effectivement, ça s'est super bien passé. Alex, tu m'as beaucoup appris du côté plus high level, où mettre les priorités, faire un travail efficace, euh, ce qui a aussi permis justement de faire tous les voyages, de rencontrer les gens, etc. Beaucoup appris côté code aussi. Merci. Et Pedro, c'était incroyable de pouvoir travailler et apprendre avec toi en même temps sur le SBI, de se poser plein de questions, de résoudre des maths au tableau. Enfin, merci pour ton temps et ta curiosité. Et j'ai beaucoup apprécié ça. Même les appels un peu informels en te baladant avec Lucas, c'est vraiment un beau souvenir, ça. Et donc, c'était vraiment un honneur d'être ta première doctorante et j'espère que on gardera contact et qu'on pourra peut-être retravailler ensemble plus tard. Donc, merci vous deux.
Faut aller faire du ski ensemble.
Mais ça, c'est pour toi. Et bon, oui, il faut que tu viennes aussi, Pedro.
Ah bah, faut qu'on fasse une randonnée ensemble à Grenoble. Ça, je suis plus partant. Et le ski,
Moi, je descends, je ne monte pas, je descends seulement.
voilà. Ouais.
Tu montes, elle monte avec toi et elle descend avec moi.
Ouais, c'est super.
Ouais. Donc,
Mais,
on se
bah,
voit
allez fêter. Ouais, ouais, je suis là, pas la semaine prochaine, la celle d'après, mais on va essayer de se voir. Je veux bien payer un verre de toute façon pour fêter tout ça. Mais faites-la maintenant déjà. Il y a un pot là pour fêter tout ça?
Oui, il y a un pot pour tout le monde.
Tu peux boire tout seul même.
Ok. Ouais, c'est ça. Je veux pas savoir qu'est-ce que tu as préparé, parce que sinon je vais regretter encore plus. Mais fêtez bien. Finis ta
Merci.
journée là, c'est fini. T'as survécu, c'est fini. Allez. Ah,
Merci. Ciao.
ciao.
Et rencontrer les super potes pour le reste, pour la suite. Et aussi ma famille. Merci d'être venu de Vienne. C'est pas à côté et Et sacré, c'est pas à côté de Paris non plus. Donc merci beaucoup. J'espère que vous savez que même si j'étais pas beaucoup là, j'aurais aimé beaucoup plus là. Et vous étiez quand même avec moi tout le temps et j'ai beaucoup pensé à vous à chaque étape dure de cette thèse et j'aurais jamais pu le faire sans vous, sans votre soutien. Merci.